am a visionary, exploring a universe of data to sharpen our view of the most distant galaxies, and studying black holes to help prove Einstein's theory of gravitational waves. I am a healer, finding a range of diseases in a sea of data, identifying lung cancer earlier and with fewer false positives, and finding new ways to bring cures to market faster. I am a helper, empowering the disabled in their homes and breaking down barriers.
She's so beautiful. Who is she?
Across languages
她真漂亮，她是谁？
and generations. I am a protector, keeping our data safe from cyber criminals and helping the lost find their way home. I am a navigator, mapping our world 1 millimeter at a time, and making even the largest self-driving vehicles safer for the long haul. I am a teacher, analyzing 500,000 player moves every game to identify strengths and weaknesses, and a learner, discovering new strategies from complex games. I am a creator, learning to paint from the masters and applying their styles to create original works of art. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere. Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
Ohayou gozaimasu. I love coming to Japan. Great people, great food, great culture, great ramen. I love coming to Japan. Thank you all for coming to GTC. GTC is for scientists, researchers, and developers whose work is so computationally demanding that it is impossible to achieve with normal computers. They seek out our style of computers because it gives them an enormous boost in the capacity and the performance of the work that they do. Over the last several years, as CPU performance has begun to slow, and yet the computational demand of their work continues to grow, GTC has expanded and exploded. In just the last 5 years, attendance of GTC has grown by a factor of 10x. It is now a global event. The number of developers of GPUs has grown by a factor of 15 times in just 5 years. And in fact, the developer architecture, the computing architecture we created 12 years ago called CUDA, and its SDK has been downloaded millions of times. And just this year, 2 million times. There's no question there is a computing movement in front of us. And yet we know that new computing architectures and computing approaches don't come together very often. It is, in fact, extremely rare. And the reason for that is because developer investment and the entire industry's investment behind a new computing architecture is incredible. And that's why new approaches and new computing architectures don't come along very often. The first thing it has to do is deliver extraordinary performance. If the performance that it delivers is only incremental, then it is better, of course, to just wait for the next generation of computers. It has to have sustainable capability that the developers in the industry needs to realize and needs to trust that every single year and every single generation, this performance advantage is sustainable and will continue. It is only then they're willing to invest in porting and developing their software for a brand new architecture. Now, hundreds and hundreds of important applications have been developed for our CUDA architecture. They develop for CUDA because the performance is excellent. They develop for CUDA because they realize that every single year, without any additional effort, the performance of their application will continue to grow. And more importantly, and the most important, is they realize that this architecture is literally everywhere, so that their customers, the people by which they write the applications for, can access the incredible work that they do. They need to know that this application can be accessed, the investment that they made can be accessed in every single country, from every single computer maker, in every single computing form, whether it's cloud, data center, supercomputer, or just PCs. Getting all of these things working together until it creates a positive feedback system so that more applications drive more computer makers to make available this architecture so that more users can benefit from it. This flywheel doesn't happen very often. In fact, this flywheel and this positive feedback system that is driving NVIDIA GPU adoption, this flywheel hasn't happened in 30 years. Today, the computing model that we used largely is still based on CPUs, with the exception of what's happening at GTC. The driving force behind the GPU that made all of that happen is computer graphics, real-time computer graphics. Real-time computer graphics has two very important characteristics that comes together in a very powerful way. The first is that computer graphics is computationally unbounded. It takes an enormous amount of computational horsepower to create an image so subtle, so beautiful, that we believe it's real. It is basically recreating virtual reality. It is basically doing physics simulation. The ultimate scientific computing application, simulating physics, generating a virtual reality that is so beautiful that we believe it's real. And yet, the second characteristic about computer graphics is that it is an enormously large market. Usually, high-performance applications are small markets, and low computational requirement applications have large markets. It is very, very rare that the two of them come together in this unique way. Computationally unbounded on the one hand, enormous market size on the other hand. The combination affords us enormous R&D budget to advance this computing form. In fact, today, no processor in the world can afford the level of R&D budget that we invest in any single generation. Billions of dollars could be invested into this NVIDIA GPU because the market size is enormous and because the computational demand is utterly unbounded. Computer graphics has come a long ways since we started. Today, NVIDIA pioneers, and we are at the core of what defines modern computer graphics. From material simulations, beautiful lighting and shadows, the reflections. Modern computer graphics is nothing short of astounding. And yet, what we really want to do is to do this completely in virtual reality so that we could put ourselves into this world. Virtual reality has been the holy grail of real-time computer graphics for a very long time. In order to achieve virtual reality, the performance has to be utterly incredible. Because the moment you move your head, you need all the pixels to move instantaneously. You need to be immersed in an environment that you believe to be real. And so what we decided to do was to create the world's first holodeck, the NVIDIA holodeck. The NVIDIA holodeck has several characteristics. The first thing, of course, is that it's physically modeled. Physically modeled means the materials are physically modeled, the surfaces are physically modeled, of course all of the geometries are physically modeled, the lighting system is physically modeled, so that it looks as real as possible. The goal is not to make it just look beautiful, it has to be beautiful. But the goal is to make it also look real. It has to simulate the laws of physics. When you touch something, you have to feel like you're touching something. When you drop something, it has to fall to the ground. Because in virtual reality, like it is in reality, you have to believe that you're touching and feeling and engaging and interacting with something that is real. You want to be able to share this world with a lot of people that are completely in different places. Virtual collaboration. The first example of virtual presence. People from different places around the world can come together in one place and feel like they're there together. And then lastly, it has to have AI. In this future, some of the characters will be real. They're your friends and colleagues from faraway places. And some of the characters in this world will be AIs. Maybe it's a robot assistant. Maybe it's just another character wandering by. Having AI in this world, helping us, collaborating with us, allows us to create just anything we can imagine. And so with that, let me show you the NVIDIA holodeck.
Hey guys, I'm Sean.
Hey guys, hi Sean. Hi Yuko.
Hi Jensen and everyone.
Welcome to the holodeck.
Okay, hey guys.
So just like
introduce yourself first of all. Who's who?
I'm Sean. I'm right here in the middle.
Hi Sean.
And this is Kyle.
Hi Kyle.
Hi.
And I'm Yuko here.
Yuko. And you guys could be, of course, you guys are all here in Japan, but you can be anywhere. Isn't that right?
Absolutely.
You can be anywhere, and you can be together in this place. And when you're in this place together, you can interact with each other. Hey, give each other high fives. And so, of course, they feel like they're inside this environment together. Sean, show us what you have in the holodeck for us.
Sure. Well, I mean, first, it's a holodeck, so it can be any place in any environment we could possibly imagine. We've built a laboratory here so that we can explore objects with realistic lightings and shadows and get a real experience and real feel for a design. Let's check out what we can do and what we can show off. So this is a Lexus, and it's the first luxury coupe from Japan.
Wow, it's beautiful.
Let's take a look inside. Kyle, why don't you hop in the driver's seat there?
Sure.
So using MDL, we're able to define mathematically how light should interact with the different properties of materials so that our car paint looks like rich car paint with multiple layers of clear coat and base coats and metallic flake if that's appropriate. If we go to the interior, Kyle can see some of the details of the leather and the other finishes that really make this design pop.
How you go. And so, of course, you could imagine designers and engineers working together on a major project together. And because these are amazing products and they're heavy products, it's hard to transport them all over the world. Wouldn't it be amazing if the Lexus is in a virtual world called a holodeck, and all of the engineers and designers can come together and just talk about it and enjoy it together?
So that's some beautiful graphics, but let's explore something that's pretty unique to the holodeck. Using our X-ray vision, we can take a look inside of the car to see the beauty that's underneath.
Wow.
We have the entire drivetrain, all the mechanics of the systems detailed out so that we can really explore it. But let's take a closer look at the engine.
Now here's the thing about the greatest thing about virtual reality. Sometimes you want it to obey the laws of physics. Sometimes you don't want it to obey the laws of physics. And now you have X-ray vision. You're like Superman.
Absolutely. Hey, Yuko, could you pop the hood for me, please?
Sure. Here you go.
Great. Now, my favorite part of the holodeck is this is way easier to do than it would be in real life.
Oh, be careful.
Now, ladies and gentlemen, what you're looking at is actually the entire design database of the Toyota Lexus.
So
Every single geometry is inside this design. Now, of course, this is not a video game. We've seen video games before, and video games could be very, very beautiful. However, video games are fake. It's not useful for design. Holodeck is designed in order to make it possible for us to really create real products inside.
And we can go deep inside of how the mechanics work as well. We can take all of this engine apart, select an individual component, and see what it does, how it fits together with the other parts of the system, and what makes the system really work.
Sean, do you know what it is?
Oh, this?
Yeah.
Yeah, this is the crankshaft.
Oh, crankshaft.
It transfers the energy from the combustion engine into the movement through the transmission.
May I take a look?
Of course.
So it is. Okay.
Oh, you're very strong.
Yeah, I am.
Well, let's clean up our mess a little bit here.
That's incredible. And so, ladies and gentlemen, the NVIDIA holodeck, and what really makes it special, give it a second. Hey, guys, thank you very much. Well, hang on a second, hang on a second. And so what really makes the holodeck special is, first of all, it ingests, it takes in the original design database of the product in all of its incredible complexities. It obeys the laws of physics, unless you don't want to obey the laws of physics. It has the ability to render the materials so physically accurately that it looks like the real material. That leather looks like leather. Bless you. Leather looks like leather. Brushed aluminum looks like brushed aluminum. Steel looks like steel. And car paint looks like car paint. Beautiful headlights look like beautiful headlights. The computer graphics is physically accurate. And then lastly, it has the ability to support virtual presence so that engineers and designers from all over the world can come together in this one place and gives you the sense of virtual presence. Hey, thanks a lot, guys. You did a great job.
Thank you.
Thank you.
Thank you.
Auf Wiedersehen.
또 만나요.
Sayonara!
Sayonara.
So, ladies and gentlemen, the NVIDIA holodeck. We can accept design databases from CATIA and Siemens and Creo and Alias. You import it into the CAD design package, is then imported into the styling package, 3ds Max or Maya. Then it's imported into the holodeck. These are all industry standard tools with all of the industry standard formats. As a result, almost anything can be imported into the NVIDIA holodeck. Once it's imported into the NVIDIA holodeck, you can have virtual reality experiences that are far and wide apart, and so that engineers and designers can come together in this environment and share it. Managers could then look at this design and be able to make trade-offs and what-ifs, try different materials and different wheels, and who knows, one of these days we'll be able to use this to even purchase and design your own car. The NVIDIA holodeck. The computer graphics industry, it's sustained with this incredible computational unboundedness, this incredible computation demand, and such enormous market size, is what created the GPU. And that GPU is the world's most advanced parallel computing processor. And then one day in the year 2012, three things came together which ignited the modern Big Bang of AI. And those three things was created as a result of a young researcher whose name is Alex Krizhevsky at the University of Toronto, experimenting with deep neural nets running on a GPU, and he submitted his results to the ImageNet contest, the CVPR contest. And as a result, he won the Computer Vision Image Recognition Contest of 2012. The achievement is utterly unbelievable. And it's utterly unbelievable because he has no special training in computer vision. And in one single stroke, he was able to defeat decades of computer vision experts with image recognition, using computers to recognize images. The network is called AlexNet. By today's standards, it is absolutely tiny. However, in year 2012, it was the single best computer vision algorithm the world has ever seen. Now, it uses a technology called deep learning. And deep learning is something that almost everybody has heard about since. In the last 5 years, it has swept the computer industry. Deep learning has been invented decades ago, in fact. However, it has one enormous handicap. Its handicap is that it requires an enormous amount of data to train the network. And it's a large network with an enormous amount of data to train, and as a result, it needed supercomputers with weeks and weeks of computation time in order to train and develop that software. It has prohibited deep learning from becoming effective until the advance of the GPU. The GPU discovered, researchers all over the world discovered around that time, that using NVIDIA CUDA GPU could train their deep neural nets in a very short period of time. A short period of time in 2012 was about a week's time. Literally, a computer would develop software by itself, running calculations after calculations after calculations for 1 week's time. The final network was the best computer image recognition software the world had ever seen. The effectiveness of deep learning was realized. The power of deep learning is that the more data you give it, the greater the network, and the greater the computational capability, the greater the effectiveness. Now that we realize the power of deep learning, we can invest and build ever more complex networks, gather more data, and build ever faster supercomputers. That the three combination, deep networks, larger networks, more data, and more compute, the combination triggered and ignited the big bang of modern AI. And the effectiveness continues to grow. Since then, amazing things have been achieved. We've now achieved superhuman recognition of images. Computer vision recognition has now surpassed human abilities. We can now achieve superhuman abilities in speech recognition. What goes in as spectral information of sound can be interpreted into natural language. What goes in as just an image could be recognized with objects and detected in the image. Image recognition, speech recognition, and so many other examples that I'm going to show you have now achieved superhuman levels. Really, really incredible. This software technique that I've simplified here has profound impacts on the industry, and it's the reason why we have dedicated our entire company, our full resources, to advance this computing field and build the AI computing platform for the industry. This year, our engineers, our partners all over the world have been incredibly busy. This is the year of Volta. Volta is the first GPU that was architected from the ground up to fuse numerical computational approaches with deep learning approaches. For the first time, it introduces a new type of instruction called tensor core, and as a result, was able to achieve a computational throughput for deep learning that has never been imagined before. 125 teraflops of deep learning training performance from just one chip. It's built from 12 nanometer FinFET, 21 billion transistors, HBM2 memory, 3D packaging. Volta, which I have one right here. Volta is the most complex chip the world has ever built. Over $2 billion of R&D necessary to build Volta. This year, Volta was announced, and it is now in full production. The NVIDIA Volta, 125 teraflops of deep learning tensor core operations per second. The Volta processor is also incorporated into a new type of supercomputer. This processor is incredibly complex. And to build supercomputers based on this processor is also complex. And so what we've done is we've integrated all of the complexity into a simple appliance to purchase, a DGX as well as a DGX station. A DGX is the world's first 1 petaflops AI supercomputers. 1 petaflops inside just one box, all fully integrated with 8 NVIDIA Voltas, connected with NVLink, which is 10 times the bandwidth of PCI Express, all integrated with software. All you have to do is take it out of the box, plug it in, and your AI researchers could be productive instantaneously. DGX. We also put Volta in every single cloud. Every single cloud service provider has adopted Volta. Every single computer maker in the world has adopted Volta because they all recognize this enormous opportunity to contribute to the future of artificial intelligence. They all recognize the enormous market opportunity of artificial intelligence. Every single cloud, every single computer maker. The software of deep learning is incredibly complex. You're talking about software that is essentially running on multiple GPUs, multiple servers, and it runs for days, if not weeks at a time. It is the largest computational problem we know today. This software stack is a high-performance computing software stack, and there are so many different types of frameworks. Framework is an artificial intelligence neural network development system. There are so many different frameworks in the world. And so what we've decided to do is optimized, integrated, and performance-tuned every single framework, every single layer of software, integrated on top of our Volta, and we containerized it and put it in the cloud. Every one of these software stacks, incredibly complicated, performance optimized, we've containerized, and we put it in a cloud registry we called the NVIDIA GPU Cloud. The NVIDIA GPU Cloud is not a cloud service. It's a cloud registry. It's a container. It's a store. It's an app store, if you will, of deep learning framework software. That cloud, NGC, each one of the containers are virtualized. And these virtualized software stacks can run on every cloud, and they can run in every server so that the NVIDIA architecture could be hybrid cloud, it could be on-prem, or it could be multi-cloud. NGC containerizes all of this complicated software and put it into a cloud registry. From training the software, this year we also announced TensorRT for inference the software. Once you're created the neural network, you can ask this neural network questions. What is this? What did I say? Where is the car? You can ask it questions. Asking the artificial intelligence network question is called inference. The computational graph that comes out of these frameworks are incredibly complex. The computational graphs are enormous. We created an optimizing compiler called TensorRT that takes the computational graph from the frameworks and compiles it for all of our products, all of our processors, Volta, Pascal, DGX, servers, cloud. And we introduced a brand new product just last week at NIPS. This is a GPU, the Volta GPU, developed for researchers. We call it the Titan V. Let me show it to you. The Titan V is the most powerful PC processor the world has ever created. Ladies and gentlemen, this is the Titan V. The Titan V. It's available online. It's available online now for $3,000, $2,999, 110 teraflops peak, nearly 10 times the performance of the highest performance GPU in the world today, called the Titan X. The Titan X was based on NVIDIA's last generation Pascal. This is based on Volta, and this is now available for researchers all over the world. And so now, the software container, NGC, will run on Volta. Go to the cloud, whatever framework you use, register for the container, downloads it, this complicated software stack, and now you're doing AI development. When you're done with that AI development, you could run TensorRT, and it will optimize the software and make it run lightning fast. Let me show you what it's like to run deep learning on NVIDIA's Volta. Thanks, Paul. So the TensorRT takes this computational graph and runs it through an optimizing compiler and outputs a Volta CUDA program. This Volta CUDA program was written by software. So software wrote software. And this Volta CUDA program for a deep neural network could predict many things. Depends on what you taught it to do. The performance that we've been able to achieve is nothing short of amazing. If you were to use TensorFlow, which is Google's AI framework, and take the output and run it on the fastest CPU for images per second, ResNet, which is a relatively small network, is 140 images per second. On V100 with TensorRT, it's 5,700. 40 times the speed up. For natural language translation, from English to Chinese, from English to German, Germans to French, all these different natural language, it's called OpenNMT, natural machine translation. A CPU runs at 4 sentences per second, and V100 with TensorRT, 100 times faster. Now, looking at bar charts is very impressive. However, ultimately, what you buy are servers. This is what it looks like when you want to run 45,000 images per second. Now remember, 45,000 images per second is not that much. And the reason for that is because you have mobile customers all over the world. You have mobile customers all over Japan. And they're maybe doing a image recognition request. They're taking a picture and saying, what is this product? I want to buy it. Millions of people are using their cell phones at the same time. And so 45,000 images per second happens all the time. And with 45,000 images per second, it would take 160 CPUs and 65,000 watts to achieve. Okay? 160 CPUs, 65,000 watts. That's basically 4 racks. 1, 2, 3, 4 racks. So 4 racks of servers would allow you to inference, predict, recognize 45,000 images per second. Well, if you were to do that with Volta, it would look like this. This is what it would look like with Volta. With NVIDIA's Volta, all it would take is one server with 8 GPUs inside, 45,000 images per second, and it only consumes 3,000 watts. 3,000 watts. 1/6 the cost, 1/20th the power, 4 racks in just one box. The more GPUs you buy, the more money you save. That is the best technology in the world. So please tell all your friends, the more GPU you buy, the more money you save. So share it with your friends. Tell your family it's Christmas time. The more GPUs you buy, the more money you save. Very simple equation. So, old way, new way. Old way, new way. Okay? So bar chart, you cannot feel it. This you can feel the servers. But now let me show it to you. This is what it looks like. Hey Ryan, are you back there? Let's show them TensorRT. Sure thing. So this is the miracle. This is the miracle of deep learning. First of all, these are flowers, of course. You recognize that these are flowers. But very few of you can recognize exactly what the flower is. Remember, the computer only sees ones and zeros. From the ones and zeros, the computer has to figure out what, first of all, that it's a flower, but more importantly, what kind of flower it is. And so Ryan, let's take a look at this. What flowers are we looking at? Okay, so that's a pincushion flower. That is a love in the mist, okay? That's a water lily, I knew that. And that's a bromelia. And that is a clematis. These are flowers, these are words that has never left my mouth before. And yet, this software can recognize these flowers. They were trained to recognize these flowers, and now, for flower recognition, this software, this program, has achieved superhuman levels. I can recognize the flower, but I don't know what it is. Now this is a CPU, this is the latest generation CPU. It's running at about 5 images per second. 5 images per second. That means 5 different consumers on their mobile phone can request, what is this flower? And in 1 second, this CPU will return the results to those 5 people. But as you know, how many people are in mobile cloud? There are millions and millions of people. There are billions of people in the world with mobile cloud capability. So this performance is obviously not fast enough. We need much higher throughput. And so we have a solution for that. Ryan, let's take a look at what it looks like with Volta. You might notice this is ResNet 152. This is a much more complex deep neural network. The other network that I showed you in the benchmark was ResNet 50, which is 50 layers of deep neural net. I think AlexNet only had about 12. The original AlexNet that was able to defeat every single computer vision engineer in the world had 12 layers. I think something like that.
8 layers.
8 layers? Okay, 8 layers, even less than 12. This ResNet 50 that I showed you in the benchmark has 50 layers. This neural network has 152 layers. Each one of these layers increases the ability and the accuracy of the software to recognize images. And now with Volta, we're running ResNet 152 at 913 frames per second. 913 frames per second, basically almost 200 times faster. Almost 200 times faster. The larger the network, the greater the speed up, the greater the advantage of the Volta GPU. But this is just one Volta. What you're looking at is this. This one chip, this one processor is making it possible for us to predict for 900 people in 1 second the object they're looking at. Imagine if we could scale this up further. Ryan? This 7,000 images per second is running on 8 Volta GPUs. So what you're looking at is this. This box right here, this is the NVIDIA DGX-1. There are 8 Voltas inside. This one box is doing this for 7,000 people. For 7,000 people. Another way to say it is it only takes 1,000 boxes. 1,000 boxes for 7 billion people. Unbelievable. Unbelievable. The more GPUs you buy, the more money you save. Okay, but the amazing thing is this. This is what's amazing. Remember, this is 2,000. This is 7,000. And the original, go back to the CPU. Take your time. And so this, remember, 7,000 is that one box. One CPU is 5. 2 CPU, which is 1 server node, is 10. 1 server node versus 1 DGX, 700 times slower. 700 times. Let's divide that by 40 for simple math, because each rack of server is somewhere between 30 to 40. So 20 racks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This entire stage replaced with 1 DGX. The more GPUs you buy, the more money you save. Okay, thank you. It's very simple. Several billion dollars of R&D, enormous amounts of invention, the more money you save, okay? And so that's Volta. Ryan, thank you very much.
Anytime.
Computer vision, image recognition was the first great breakthrough of deep learning, and it inspired everybody to think about what else is possible. We were so fortunate in our company to recognize the potential of deep learning, and several years ago, we started to invest and started to do research in deep learning all over our company. First, we created the platform that allows us to have the most powerful platform, most productive platform that's literally everywhere for deep learning researchers. But we used the platform ourselves to advance deep learning so that we could see what are the unsolvable problems. What were the previously unsolvable problems that we can now solve? It is so exciting that for the first time in all of our careers, in 30 years' time, we now see this new tool, this incredibly powerful tool that allows us to solve problems we simply could not imagine solving before. Now, this is really an amazing thing. This is ray tracing. This is a form of computer graphics that creates photorealistic results. It is very, very slow, even on the fastest supercomputers. It's called ray tracing and global illumination. What you're looking at here is, on this side, each one of the pixels are slowly being rendered as the rays bounce off the surfaces, eventually comes to our eyes. But there are many black dots. The black dots is the photon has not reached it. Using artificial intelligence, our NVIDIA researchers were able to predict what is the right color, what is probably the color of that dot. And as a result, we can complete the image almost instantly. Second, NVIDIA research worked with Remedy, a game developer, to do something that is really, really hard to do. To create animation, computer-generated animation that looks like they're talking. But unfortunately, there's so many things that we say, and there's so many different types of faces. How do we teach computer graphics animation to speak and to look like it's speaking? So we developed a network that allows us to use audio to automatically generate the appropriate animation of the face.
皆さん、こんにちは。GTC ジャパンへようこそ。 僕の言葉を理解できますか？よかった。GTC シリコンバレーの後、日本語をずっと練習していました。どうですか？うまくなったでしょう。それにしても、ジェンセンさん、その革ジャン、かっこいいですね。
Every single phrase you give it, the character will animate in a new way because it has learned how to animate properly. This is using computer graphics first to create a segmentation of semantics. What is the meaning of every single pixel? And from the meaning of the pixel, we will generate a photorealistic image. So, computer graphics generated image input. The output is photorealistic images. Okay? So, first we start with computer graphics. Every single pixel has been given a meaning, otherwise known as semantics. What is that pixel? This is a pixel of road. That's a pixel of car. This is the orientation of the car. This is a pixel of tree. This is a pixel of people. And the background, the gray, is pixel of buildings. And for each one of those pixels, you can see there's an orientation, a pose, the pose of the car, the pose of the people. From that, we gave that input to an artificial intelligence network. And the network has to draw, to image, to generate a photorealistic image. Unbelievable, right? Okay, so let me just show you. This is the input. We use computer graphics to generate a segmentation and a semantics map. From this map, we create a photorealistic image. The artificial intelligence network drew this image by itself. The artificial intelligence network generated this image by itself. This next one is just incredible. This next one, most artificial intelligence network called a GAN, which is a breakthrough by a researcher called Ian Goodfellow. GAN stands for Generative Adversarial Networks. It's basically a neural network that knows how to create the future, create something. In this case, we asked this neural network to create an image. Unfortunately, GANs are very difficult to control. If the GAN is too big, if the GAN is too small, the resolution of the image is too coarse. However, if the resolution requirement is very high and the GAN network is enormous, then the stability of training is very low. This balance was very difficult. NVIDIA invented this new GAN called progressive GAN. The more you train it, the larger the network becomes, and it's eventually able to generate every single pixel of this face. We then take celebrity faces, and we trained our network to generate new faces. These faces do not exist. These are not real faces. These are artificial intelligence generated faces. And AI created this face. And it created these faces. Every single image, every single pixel was drawn by an artificial intelligence network. Pretty beautiful, huh? Not only is it realistic, photoreal, the resolution is incredible, and it's very realistic. Using artificial intelligence, we can now generate and create artificial humans. We can use artificial intelligence to make the artificial humans talk. And we can put them into artificial intelligence created worlds. Incredible. What do you guys think? Artificial intelligence was responsible for the introduction music that you guys heard. It's called I Am AI. We created recently a new piece of music. As you know, it is Star Wars time. And I understand, I have tickets for Tuesday night. I'm so excited to go see it. artificial intelligence was used to do something very special here. What we did was this. IVA and NVIDIA worked together on a neural network that learned the composition techniques of traditional classical great composers, Mozart, Bach, Beethoven. It learned classical music. So it recognizes, it knows how to generate the next note given previous notes, what the appropriate next note would be for classical music. Then we gave it some new artistic styles. And the artistic style we gave it was John Williams. I selected several beautiful pieces of scores of John Williams. And with John Williams' scores, we additionally trained and we biased this network to generate something that John Williams might create. What I'm about to show you is an original piece, never heard before score, generated by artificial intelligence. This original score is then given to a symphony. And the symphony we worked with is John Beals, the famous John Beals in Hollywood Symphony Orchestra. And he arranged and conducted what you're about to see. This score is an original piece completely created by artificial intelligence. Enjoy. John Beal and the Hollywood Symphony Orchestra.
2, 3, 4, 5.
What do you think? Incredible, right? Artificial intelligence was able to generate this beautiful music, and working together with human orchestra, we could bring it to life. This is the future of software. This is the future of computing, where computers could write software by itself that is so complicated no human could possibly imagine writing. And by working with humans, it makes possible new realities. Our mission, first and foremost, is to create a computing platform that is powerful, for training and inference that accelerates every single framework that's available in every single cloud, on-prem and from every single computer maker, and just one architecture. One architecture so that all of your investments in software will be leveraged across this entire base of platforms. One architecture so that every computer maker can put their full might behind this architecture and know that there's a large market for them. And one architecture so that all the work that we do today will continue to benefit tomorrow and the day after and the day after. The work that we do today will just get more valuable every single day because the architecture will continue to be backwards compatible and the architecture will continue to grow. One architecture, the NVIDIA AI platform. NGC, all the software in the cloud, and it can run in every single cloud. It is multi-cloud. Amazon, Google, Azure, Baidu, Alibaba, Tencent, every single cloud. It runs on-prem, and it runs on the Titan V in a PC. The most pervasive AI computing platform in the world. AI is the most powerful force that anyone has seen in all of our careers. And I feel that it is also the most powerful technology force that has finally the benefit of revolutionizing the industries of Japan. I've had the benefit to see the server revolution, the workstation revolution, client servers to PCs, to mobile to cloud. But PCs can't help the car. A cell phone can't help robotics. And the cloud can't help large, heavy industry construction. Japan is the land of robots. This is the land where the companies, the leaders of this country, are the world leaders in transportation, the world leaders in manufacturing robotics, the world leaders in heavy industry and heavy construction, and surely applying that robotics technology to the future of healthcare. Whereas the IT industry moves bits, the industry of Japan moves people and it moves earth. Very large challenges. The fundamental technology necessary for these industries, as it turns out, is not PC, it's not mobile, it's not cloud. They're all important, but the fundamental technology that's necessary is artificial intelligence. And that's why I am so incredibly excited now for the future. That's the reason why this is such an incredible time for Japan. This is the golden ages of IT technology in Japan. And we're incredibly honored to partner with some of the best technology companies in Japan, the most important companies in Japan. Let me introduce you to some of the work that we're doing. We partner with Fujitsu, the #1 computer company in Japan. Yoshizawa-san, the head of Zenrai, has worked with us closely to adopt the NVIDIA Volta into the Fujitsu servers. A heritage of supercomputers, the largest IT company in Japan, is now with 200,000 professionals serving this nation. We're now partnered with them to bring the NVIDIA AI computing platform throughout Japan. NTT Communications is the #1 cloud service provider in Japan, has now also made available NVIDIA Volta, the NVIDIA GPU, in their cloud. The Advanced Industry Science and Technology Institute, AIST, responsible for some of the great breakthroughs in collaboration between science, government, and industry, has adopted the NVIDIA architecture to create the highest performance supercomputer for AI in the world. 550 petaflops, almost 1 exaflop It is the closest computer to 1 exaflops of computing for AI. 0.55 exaflops. 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 Exascale computing. We thought would not happen for another many years. And now, AIST partnering with us to build the ABCI supercomputer. Sekiguchi-san is leading that effort. Inaba-san and I, Dr. Inaba-san and I, announced last year that Fanuc, the world's leading manufacturing robotics company, would partner to create a new type of AI for manufacturing. Fanuc's famous field system is now infused with AI so that it could predict downtime in advance so that customers have zero downtime, that has the ability to teach robots how to bin pick, and has the ability to detect very minor surface defects long before it affects the products. Fanuc, with Field incorporating AI, is now powered by the NVIDIA GPU. It was announced and shipped just this October. Incredibly proud of the work that we're doing there. PFN, Preferred Networks. A young startup with a genius CEO, Nishikawa-san, who is working on AI all over Japan, and has created an excellent framework called Chainer. Chainer has been able to train a neural network in 15 minutes across 1,000 NVIDIA GPUs. Distributed training was able to create and train this neural network in literally 15 minutes. The amazing thing is this neural network, the ResNet 50, would have taken 1 month just 3 or 4 years ago. Just 3 or 4 years ago, it would have taken 1 month. And now, with all of our collaboration, the advancement of NVIDIA GPU computing, we're able to now bring down training time to just 15 minutes. The power of doing that is really profound. As a result, researchers could iterate and explore new ideas more quickly. But one of the most powerful new ideas is to use AIs to create AIs. Using AI to create AI. So in the future, there will be another AI that sits on top of these frameworks. And it will invent new forms of AI that is then trained and tested for effectiveness. So the fact that we can take training time down to 15 minutes is an incredible achievement, and we need it. And our partnership with PFN also resulted in us putting the PFN Chainer network fully optimized, fully tested, and containerized, and now put on the NGC, the NVIDIA GPU cloud. Ichimura-san and his researchers at University of Tokyo are doing some amazing work. In fact, the researchers here in Japan has contributed 55 groundbreaking works into AI this last year. Ichimura-san and his team did something really quite amazing. This is one of the futures of scientific computing, where scientific computing, numerical computing, physics-based computing is fused with machine learning. Physics-based computing, first principle-based computing, algorithmic computing can accelerate the discovery of new science. Ichimura-san's work is related to earthquake simulations. It takes a long time to simulate an earthquake. But combining and fusing these two approaches and using NVIDIA GPUs, they were able to accelerate their training time, their discovery time dramatically. There's so many startups here that we're working with. Some 60 startups here in Japan. 60 startups. From PFN to Abijay, who's also developing a deep learning framework. Wizard. Wizard. I think it's an exoskeleton company that's teaching robots how to articulate. L-Pixel for medical imaging. There are so many companies here doing amazing work. Many of them doing work in the field at the intersection of artificial intelligence, robotics, and manufacturing and industrial designs, industrial products, industrial machines, which makes perfect sense because that's the industry of Japan. As you can see, AI from the most important companies, computing companies, Fujitsu and Entity Communications, to the Research Institute, AIST, to the world's leading manufacturing robotics company, to AI startups, PFN, to research. Groundbreaking work is being done here in Japan at this intersection, AI and autonomous machines. Autonomous machines is really the next generation of AI. It's the next step of artificial intelligence. And the first contribution of artificial intelligence to autonomous machines will be the self-driving car. The self-driving car is going to change society completely. It's going to make possible, of course, cars that are easier to drive, safer to drive. We will save lives. But because of the nature of autonomous cars, long term, the car will no longer be a place that you go so that you can go to another place. Long term, the car will be the place we want to be in for some time. Each day, we would enjoy our 1 or 2 hours of personal time inside a car. It is our time for relaxation. It is our time for entertainment. Because of the autonomous car, other urban design decisions will likely change. The shape of transportation and the shape of society could very well change as a result of this groundbreaking work. Autonomous vehicles is incredibly hard to do. However, the impact of society is gigantic and enormous. The problem is simply stated as the most challenging computer problem the world has ever seen. It is rich with high-performance sensors. The software has never been developed before, from very complex system software, computer vision software, artificial intelligence software. The algorithms have never been developed before. This car with this computer can never fail. It's not like your cell phone. It's not like your PC. You can't hit Control-Alt-Delete. The car has to be perfectly safe. And it has to be able to navigate and drive and operate in such a diverse and complex world. The self-driving car is simply the most complex computing project the world has ever undertaken. It is also a software-defined computer. The number of applications that we have to write is really countless. Whereas the previous way of designing cars is to connect many specific functionalities into a car. The future autonomous driving car, the future car, is surely a software-defined car with a powerful computer, a capable, functional, safe operating system, incredible algorithms, and all kinds of applications on top. The same thing that happened to the mobile industry when it went from being a cell phone to a mobile computer, from one application, just camera, to thousands and hundreds of thousands of applications in the App Store today. The same thing will happen to the car. The complexity is enormous. From level 2, where the car is basically the autonomous vehicle is helping you drive, but you're in control, to a level 3 and level 4 car, where the car is in control whenever it knows how to drive in those conditions, to a level 5 robot taxi, where the car has no driver at all. And its functionality directly affects the economics of the service and, of course, the enjoyment of the users. The range of autonomous vehicles is really quite daunting. And every single car company, surely every single major car company, has to create the entire line of cars. They need to have a scalable architecture that allows them to develop software that is largely related for a range of cars. As the sensor complexity grows, the functionality grows, and of course, the functional safety requirements continue to grow. This entire range of capabilities has to be developed in an architectural sense, and you have to think about it from a software level. We created a computing platform we call the NVIDIA Drive. The NVIDIA Drive is a supercomputer on a chip. A supercomputer on a chip. And it's able to scale to level 2, level 3, level 4 to level 5. It is able to understand the type of functionality. It includes sensor fusion, computer vision, deep learning, high-performance computing, in a very small energy-efficient package so that it's able to perform all of these different types of applications at the same time. It has to run them all at the same time in a very high-performance state so that the car can be as responsive as possible to all of the environment around it. And it has to do so from level 2 with just maybe front and surround cameras to robot taxis with tens of cameras and LiDARs and ultrasonics and radars all around the car, because downtime is simply intolerable. And so the range of functionality, the range of sensor richness, and as a result, the scale of computation necessary is really daunting in this new world of autonomous vehicles. We've been working on this technology, and I want to show you some of the work that our engineers have done. They've made a whole movie for you, and so let's run it. Using deep learning, we're able to recognize the world around us. What are the objects we should avoid? It also recognizes what are spaces that are safe to drive. We have to figure out what is the trajectory of our car using cameras or using LiDARs. The future self-driving car computer has to be able to process sensors of all different types. It has to localize even to a sensor we call the HD map. Localizing allows us to then drive using computational approaches or deep learning approaches. Surround perception in all kinds of different weather conditions, rain, snow, highway, urban. One of the powers of artificial intelligence deep learning is the ability to train one network, and it now recognizes the objects around it. Ladies and gentlemen, the NVIDIA Drive. Autonomous driving will revolutionize cars, but AI will revolutionize not just driving, but also our user experience. Remember, we now have sensors all around the car. We're going to have sensors and cameras around the inside of the car. So this car, our future cars, will have contextual awareness of the world around us, and it will have contextual awareness of us. So the question is, what can we do with artificial intelligence, computer vision, augmented reality, and how do we fuse those fundamental technology to change to revolutionize how we enjoy our car. And we think that in the future, not just the inside of the car, not just the outside of the car, the functionality of the car will be revolutionized, but how we enjoy the car and how the car interacts with us will be revolutionized. The amount of software that we have to write, is really quite boundless. And we've imagined several applications we could create. And so what we've done is we created a SDK that fuses the sensors of the cameras outside the car, the sensors and the cameras inside the car, and we created a brand new SDK we call the Drive IX, Intelligent Experience. Drive IX is an SDK that software developers all around the world could then create the next generation of user experience. Drive IX includes eye tracking, head pose estimation, speech synthesis, speech recognition, gesture recognition, facial recognition, fundamental technologies that are then used to create next generation applications. Let me show you some examples. This is Janine, one of our employees. And here's an example where she's coming back from an airport and she's carrying all these different bags, and she could be coming out of a store, and the car sees her, recognizes her face, and opens the trunk. Of course it should. Your car is an AI. Of course it should. There's other things that it could do. It tracks your eyes. We use artificial intelligence, deep learning, and a very special technique for labeling. We can now track eyes very carefully. And so this way, we know that as we come to a stop, that somebody who's crossing the street has made eye contact with us before we decide to go further. So wherever she looks, we can calculate and estimate what is the angle of her eyes. And remember, we're doing this only from two-dimensional cameras. How do you predict the path that you're looking at, the orientation that you're looking at, just from a video? Here, we're detecting that she's being distracted. So we wrote a small application.
Distraction.
And so, if you have a car and the car's driver is required to be in control, we could create an AI that allows us to remind you that you're distracted. We can create an AI that recognizes that you're sleepy and that, in fact, you should probably have a cup of coffee or pull over. This is Janine pretending like she's sleepy.
Attention, wake up.
So all of a sudden, this car is no longer just an autopilot, but it's also a co-pilot. A co-pilot that watches after you while you are the pilot in command. And then lastly, remember, this car has perception all around it, surround perception. And so how many times have you tried to get out of a car and you shouldn't have?
Caution, just a moment. All clear.
If a car is coming, if a bicycle or a person is coming, the car door simply doesn't open. And so this car is not only driving for you when it can. When you're driving, it's also watching out for you. And so as you can see, the future car is just rich with software. And we need a basic computing platform that is able to do the type of processing necessary for the future autonomous machine. And the autonomous machine basically has to do three things. It has to do sensor fusion, sensor processing and sensor fusion. It has to do artificial intelligence and parallel computing. Artificial intelligence and parallel computing. And it needs to be able to then take that information and take action, recommend an action. Autonomous machines in the future has these basic capabilities. These basic capabilities is basically a supercomputer on a little tiny chip. Much, much more powerful than any computer that you currently have that you own. And so this new computer requires a new type of processor. And in addition to that, this new computer has to be programmable because there are so many applications we can imagine. every single week, your engineers are going to create more and more and more applications. You're going to put them onto the store, and you're going to download it into your car, and the car gets smarter and smarter and smarter over time. So we believe that the future car is software-defined. We believe that we need to have an architecture that can run these type of applications. And we believe that we have to create a computing stack for the industry so it can take advantage of these capabilities. The first thing that we have to do is to invent the processor. And so what we did was we created Xavier. Xavier is the most complex chip NVIDIA has ever created. Even though this is the largest, even though Volta is the largest, Xavier is the most complex. The number of engineers that have worked on Xavier to create the world's first autonomous machine processor is in the hundreds. I'm happy to say that Xavier is coming out of the fab momentarily, and I can't wait to put it in the hands of autonomous vehicle partners, car companies, roboticists, autonomous machine makers all over the world. Supercomputing capability, computer vision capability, deep learning capability, rich with sensor processing abilities, all in just 30 watts. 30 watts of power, 30 trillion operations per second. 30 trillion operations per second. Incredible amounts of performance. We also created Xavier so that it's a scalable architecture. You could use one chip, one Xavier processor for your super level 2 with surround perception and all of the capabilities I've just described. You could also use multiple Xavier so that you could have more sensors, functional safety for redundancy and resiliency, or if you have tons of sensors all over the car, you could use a computing platform we call Pegasus with multiple Xaviers and multiple GPUs in one computer. As you could see, the future of autonomous vehicles is about supercomputing for real-time processing of the world. It is a brand new type of computing, but with something like Xavier and the software platforms we're developing, application developers all over the world can create the next generation of magical cars. Now, creating the car starts with developing the software. And even developing the software is intensely different. For those who are already working on deep learning, you realize that the way that deep learning is done is very different than the way that software development was originally done. In the world of deep learning, and here I'm using the example of a self-driving car, you use 3D simulation to simulate the extreme cases that the car would experience. We have a training supercomputer. To train and recognize the millions and millions of images that we are going to provide the neural network. We use a supercomputer to regression test against a large body of tests before we can release software. We call that resim. And then when we're done, the final neural network could be run in Xavier in the car. Altogether, that represents the end-to-end. In the future, data is the source code. Data is the source code. And so it stands to reason that in the future, we need to have a rich infrastructure to manage, to track, to curate, to process, and to reprocess terabytes and terabytes and petabytes of data that we will collect. The future of computing is radically different. If your engineers and IT department would like to learn more about this, reach out to us. I'd love to talk to them about it. This future computing platform is really worthwhile to take a look at, and we've invested a great deal in this. Well, this is the era of autonomous machines. The self-driving car is the first one. It's the first and the most impactful to society of the autonomous machines we can create, but there's so many more. I believe that every single machinery that moves will have autonomous technology in the near future. It could be an excavator. It could be a plow. It could be a truck. It could be a dump truck. It could be a tractor. It could be a robotic arm. It could be a little tiny robot that's helping you manage your warehouse or delivering pizza to you, delivery pizzas. And so all of these different types of machines in the future will have autonomous capability. The fundamental computing is the same as a self-driving car. but the application is radically different. The applications and demands of it is radically different. In many of these types of examples, the actual processing, sensor fusion, sensor processing, deep learning, artificial intelligence, reasoning, and then actuation is fundamentally the same as self-driving cars. We believe this is going to be the next era of AI. And the opportunity to the market is quite large. $400 billion autonomous machines market, from manufacturing, agriculture, industrial, construction, to packaging and processing. Enormous markets. Now, the future that we imagine is a world where the entire construction site, in the case of heavy equipment, is completely reimagined. We're going to have drones in the sky that is scanning and mapping the construction site. Every single one of the heavy machinery will be autonomous, and it will be able to recognize the world. It will use SLAM to scan, to localize and map its surroundings. And through its surround perception capability, it will keep the operator, it will keep all of the construction workers out of harm's way. It will be easier for the operator to manage this very large equipment, and it would even learn from the operator how to do certain tasks. These future autonomous machines will extend the usefulness of these autonomous machines and these very expensive heavy equipment, and will also, very importantly, improve the safety of construction sites. One of the things that we're really excited about is the possibility, of course, of uniting artificial autonomous machines with the work that we're doing with holodeck. It is possible for us in the future to fuse the minds of machine and people, to literally fuse them together using virtual reality and artificial intelligence. A person, an operator, could be miles away inside holodeck, and yet the operator will think that he or she is literally inside the equipment in the construction site. The autonomous machine will scan and beam the world to the operator. The operator will operate the virtual instrument, the virtual equipment, and the commands will then be beamed back to the autonomous machine in the field, and now the two are fused together. Using virtual reality and artificial intelligence, we could fuse autonomous machines and humans. This future world is really, really exciting. And I'm incredibly excited to say that the leading industrial equipment company in Japan, Komatsu, and NVIDIA are partnering together to discover this future. Dr. Iwamoto, the CTO of Komatsu, is leading this charge to invent the future of industrial equipments, to invent the future of construction. Fusing AI, fusing 3D, fusing mapping, the type of technologies and experiences we can create is really quite exciting. So I'm super excited to announce that we're partnering with Komatsu, a 100-year-old company, one of the world's great companies, one of Japan's great companies, is now inventing its future, inventing the future of autonomous machines. I'm super excited about that. This is the land of robots, and you can just tell from IREX, the land of robots. Every 2 years, IREX, the International Robotics Expo, hundreds of thousands of people come together. This year, there were 200 industrial robot companies showing robots, 150 service robots, new companies showing robots, and there were robots of all kinds, and we're doing robotic things of all kinds. They're serving beer, they're making salad, they're folding towels, picking up a car like it weighs nothing, lifting it up in the sky. That's the Fanuc robot. Inaba-san's robot over there. This is a service robot helping somebody in a hospital. This is Sota. Sota is a little tiny social robot that talks to you. This is a Toyota robot that is working on articulation. This lady here is really interesting. HRP4C. Her name is HRP4C. She is the girlfriend of C3PO. Autonomous humanoid robots. There are all kinds of robots. They're making salads, serving beers, and they're all learning how to be robots. The future of robots is surely bright, and as you can see, we're going to infuse artificial intelligence into all of it. The challenge of robots is unique. Unlike a deep neural network that learns how to recognize speech, where you give it a ton of speech and it simply tries and tries and tries and tries until it gets better and better. In the case of self-driving cars, we teach the self-driving cars how to avoid the world around it, how to stay in the lane, and what rules to follow. In the case of robots, and remember, the self-driving car's mission is simply to avoid obstacles, Teaching an autonomous machine how to avoid obstacles is fundamentally different than teaching an autonomous machine how to interact with obstacles. The interaction with the world is a fundamentally new problem to solve. It is incredibly complicated. To interact with the world, you have to be able to, of course, perceive the world. You have to recognize the physics of the world. Maybe what you're trying to lift is too heavy. Maybe your grip is too strong. Maybe the object is too slippery. Understanding the physics of the world is a very complicated thing. And yet, the articulation of our digits is something that we don't know how to write programs for. So how do we write programs for all of these computers? And so the question is a deep one. We believe there are three things we have to do. The first thing that we have to do, of course, is to build a processor for autonomous machines. We know that every single one of these autonomous machines will have sensors, cameras, 3D cameras, depth cameras, LiDARs, sonars, pressure sensors, temperature sensors, sensors of all kinds. The second thing we know is that these autonomous machines will all be powered by AI. And the third, that AI has to actuate motors of tremendous complexity. Not just 6 degrees of freedom, not just 2 degrees of freedom, but 20, 30, 40 degrees of freedom. Basically, every degree of freedom. That level of complexity is some AI that we simply don't know how to write. And so we imagine that the third component, the third pillar of the future of autonomous machines is to create a virtual world. A virtual world that looks like the real world. A virtual world where robots can learn how to be robots. A virtual world that obeys the laws of physics. So that when we're done training this robot in a virtual world, we can take the brain and move it out into a physical robot. And that physical robot will know exactly what to do. That physical robot will be born. This virtual world we call Isaac. Isaac is a future world where a robot is learning how to be a robot. So this is Isaac. We named Isaac after Isaac Newton and Isaac Asimov. Hi, Isaac. Isaac has eyes. The eyes of Isaac, the sensors of Isaac, will be programmed. And ideally, it will mimic the real sensors. The Isaac eyes will see the world that is computer generated. So it will learn the neural networks necessary. In this case, what we're teaching Isaac how to do is golf, as you can see. Right now, Isaac is not super good. Okay, it's looking at the ground, looking at the ball, and it's trying to learn how to play golf. Now, let me show you how Isaac first started to learn. Let's go to the beginning. In the beginning, Isaac doesn't even know how to hold the golf club and what it means to putt. However, whenever it touches the ball and the ball moves in the right direction, we told Isaac, good job. Every single time it does something smart, we give it positive reinforcement, just like a child. And Isaac tries and tries and tries, and every time it does something good, we say, good job. And then it tries for a long time. Let's move forward a little bit, Jeffrey. There it looks like it's stir-frying. Okay, Jeffrey, we'll move forward a little bit. After Isaac trains for a very long time, it's getting smarter. A little further, please. Okay. And after a while longer, wow. Wow. Artificial intelligence never make mistakes. Wow, wow. Okay. Now, you know, the green, oh wow, look at that. The green is not flat because the green obeys the laws of physics. Okay, one more. We'll just see. It's just too mesmerizing to watch. Okay, all right. Good job. Thank you. Thank you, Isaac. Good job. So we create a virtual world where the hardware mimics the hardware, simulates the hardware of the physical world. The processor, the sensors, the actuators. We then use artificial intelligence in this Isaac world to train, to teach Isaac how to be a robot. Today we're teaching Isaac how to play golf. In the future, we'll teach Isaac how to fold clothes, how to fold towels. In the future, we'll teach Isaac all kinds of things, how to put pieces of things together, how to manufacture, how to work next to us. I could be inside in a holodeck, and I could say, Isaac, pass me that screwdriver. And Isaac will go, pass me a screwdriver. And someday, when we come into the physical world, I tell Isaac to pass me the screwdriver. Isaac will pick up the screwdriver and hand it to me. This virtual world has to allow robots how to learn to be robots without destroying everything. And this virtual world needs to behave at super real time because we want to teach the robots as fast as possible. This is just an incredible time, ladies and gentlemen. We're looking at a technology, deep learning, that has made it possible for software to write software, for computers to write software that is so complicated that no human can write. And now, the computer is starting to become an artificial intelligence. This artificial intelligence has proven to solve many problems, from image recognition, speech recognition, natural language translation, to even generating music, generating photographs, generating virtual worlds, generating art. It is used for diagnosing medical images for radiologists, for pathologists to detect early signs of cancer. Deep learning is now spreading throughout every industry. And here in Japan, I'm so excited that deep learning has the opportunity to revolutionize the future of manufacturing, the future of industrial equipment, the future of robotics, and help create the next generation of autonomous machines. This year has been super busy for us. We started by creating the fundamental platform. the fundamental platform we call NVIDIA AI. It is multi-cloud, it is hybrid cloud, it is the most powerful training system in the world, and it's the most powerful inference system in the world. It is available all over the world. It is the most accessible AI computing platform anywhere in the world. We call it the NVIDIA AI. The next part is NVIDIA Drive, where we apply this computing platform ourselves to solve a very difficult problem. And this difficult problem, called autonomous vehicles, we believe is software defined. The number of applications we have to create for the future of autonomous vehicles is uncertain, and in my opinion, unbounded. The future car is going to be a computer on wheels. And the type of applications we will write for the future of cars, we haven't even imagined yet. Our job is to go explore that with you, explore that future with you. The first part is to create the computing platform. We call it NVIDIA Drive. NVIDIA Drive has a brand new processor called Xavier. It's a little tiny computer. It is scalable from level 2 all the way to level 5. One architecture. The autonomous driving stack is called Drive AV. The intelligent AI is called Drive IX. The entire SDK is open. Software developers can then take advantage of all these capabilities to create the future car. It is an open and scalable platform. The future of AI, the next major revolution, is autonomous machines. And I can't imagine a more appropriate place than Japan to invent the future of autonomous machines. The most important companies in the world in machinery, the world leader in manufacturing robots, Fanuc, the world leader in industrial equipment, Komatsu. Both of them, I'm so grateful and so honored to partner with them to invent the future of autonomous machines together. And then lastly, AI in Japan. The world leaders, leading companies here in Japan, Fujitsu, NTT Communications, AIST, working together to advance AI computing here in Japan. I want to thank all of you for coming to GTC. This is really an extraordinary time, and it's a great honor to partner with all of you to create the future together. Thank you.